All right, let's take a look at this example. We have a coupled system of differential equations here. So x and y both depend on t. X and y are my dependent variables. T is my independent variable. And the derivative of x depends on both x and y. If this guy only depended on x, if we didn't have this 3y here, we would just solve it using, it would just be a linear dE. We would just solve it. But this system is coupled. We'll learn later how to sometimes uncouple DEs and solve them separately, but that's not what's happening here. Okay, first thing we want to do is write this in matrix form. So we are going to define or call the vector x to be the xy. So that's a capital X, that's a lowercase x. Let me make sure this guy here looks lowercase as well, because that kind of looked like an uppercase X there. There. So the vector X, sometimes people have trouble with my handwriting there. When I'm writing that, what I'm writing is an arrow representing a vector. So that is a vector X and it's XY. Then vector X prime would just be X prime, Y prime. And then we could write this equation in matrix form. That's your first step. And that would be the vector x equals, what was it, 2, 3, 2, 1. Prime vector x. Okay, now we're going to find our eigenvalues and eigenvectors. So our eigenvalues, we do a minus lambda I, and we take his determinant. A minus lambda I means subtract lambda along the main diagonal. So that will be 2 minus lambda, 3, 2, 1 minus lambda. And remember, absolute value bars here means I'm doing a determinant. So just along the main diagonal, minus lambda. Leave the other guys alone. That's supposed to equal 0. Remember to do a 2 by 2 determinant, multiply this way minus that way. So 2 minus lambda times 1 minus lambda minus going this way, 6 equals 0. All right, let's clean this up. This is where mistakes happen, by the way. Just simple arithmetic mistakes. What do we get? We get 2 minus 2 minus 1, so minus 3 lambda plus lambda squared minus 6 equals 0. So that's lambda squared minus 3 lambda minus 4 equals 0. That factors. If you can't factor that immediately in your head, you're not very good at factoring. Get better at it. We get 4 solutions, 4 and negative 1. Let me pause and make sure that was right before I get too far in this. Okay, so we got our 2 eigenvalues. All right, now we find our eigenvectors. Each eigenvalue will give us an eigenvector if they're distinct. If we have repeated eigenvalues, if you get the same thing twice, then there's this whole process. That's a completely separate video. Like, it's a really complicated process. But we have distinct eigenvalues. We're happy with that. So lambda equals 4. Remember, I showed you in the last video 2 different ways to find your eigenvectors. The easy way is a minus lambda I times your vector k should equal the 0 vector. Don't forget that this is a vector over here. Okay, so what's a minus lambda I? Take your matrix A, 2, 3, 2, 1, and subtract lambda along the main diagonal. So here, minus 4, minus 4. And that's times the vector k1, k2 should equal the vector 0, 0. All right, so what do we get here? We get negative 2, 3, 2, -3. You should always check. Sometimes it's not completely obvious, but every single time when you've done this step here, this row should be a multiple of this row. That's what made this determinant 0. If that's not the case, you've done goof somewhere and you need to go back. You always got to check this. I mean, look, if I take row 1 times -1, I get row 2. That's how you know you got yourself an eigenvalue. So once you've checked that, we only need top row. We only need the top or the bottom. We only need one of these two equations. These two equations are, take this row times this vector. Don't forget to put the plus in between. And that should equal the top guy. Or the bottom row. 2k1 minus 3k2 equals 0. That's from the bottom. Either one, it's the same thing. Don't try adding them together. You're going to get 0 equals 0. Don't try elimination, substitution, none of that. We just want one of these, but you should always check that they are in fact giving you the same information. I kind of like this second one better because when I move this guy over, I don't have to deal with any negatives. So this guy says 2k1 equals 3k2. Now you're always allowed, if you want, you can just say k1 equals 7, whatever, and then solve for k2. You can make up one of these and solve for the other. But I don't want to deal with the fractions. So I think the easiest way, get in this form and then swap coefficients. So k1 will be 3, k2 will be 2. Then look what we would get here. 2 times 3 is 6. 3 times 2 is 6. So for lambda equaled, what were we on? Lambda equals 4. His associated eigenvector, we'll call him k sub lambda equals 4, is the vector 3, 2. Now we find the other eigenvalue. What was -1 was my other eigenvalue. And we find his eigenvector. So what was the 2, 3, 2, 1? Is that what my matrix was? 2, 3, 2, 1. So again, just for completeness, I want 2 minus -1. Leave the 3. Leave these two guys alone. Along the main diagonal, do whatever you had minus lambda. So minus a -1. And that's going to be times k1, k2 equals 0, 0. Now, I mentioned this in the last video, so real quickly, I know I've already used up the letters k1 and k2 right here, but that work is done. Those guys can go back in the pile now. I'm allowed to recycle those. As long as I keep my work separated, I know I'm not going to confuse myself. If you're worried you're going to confuse yourself, give these unique names. All right, so what do we get here? We get 3, 3, 2, 2. Clearly not independent rows. One is, if I multiply the first row by what, 2/3, I get the second row. So you always want to check that. Always check and make sure. If I had gotten this, I'd know I goofed somewhere. Because now the second row is not a multiple of the first row. Okay, so I only need the top row. 3k1 plus 3k2 equals 0. Move this guy over. And then I could play the swap coefficients games, or like I just like smaller numbers. I'm going to cancel out the 3. Boom, boom. k1 equals -k2. So like I could make it anything. I could make it 7 and -7, -35 and 35. I'm going to go with 1 and -1. Doesn't matter where I put the negative either. Any multiple of an eigenvector is still an eigenvector. So the eigenvector associated with lambda equals -1, we'll go with 1, -1. Okay, now we're pretty much done. My general solution is x equal x vector C1 k from the first lambda, lambda number 1. I'm just writing this in general. E to the lambda number 1 t plus C2, my second eigenvector, e to the second eigenvalue, t. And who I call first and second, by the way, if I'd done these in the opposite order, who cares? All that's going to do is you're going to change who you call C1 and C2. Okay, so I get C1, I've already forgotten what was 3, 2, e to the 4t plus C2. I think I went with 1, -1, e to the -1 t. So there is my solution written in vector form. Now let's write it out in like component form. So remember the vector x, I'm going to write that nice and pretty. It's vector x was the vector xy. So all along the top is x, little x. 3c1 e to the 4t plus 1c2 e to the -t. And all along the bottom, 2c1 e to the 4t will be my y, minus c2 e to the -t. Now this, our solution here is still coupled in terms of c1 and c2. I've seen this mistake happen, so real quick. You might look at that and go, oh, 3 times c1, that's just a new c. I'm going to squish that together into a new constant of integration. You can't do that because I have two equations that have c1 in them, two equations with c2. You can't squish that 3 and that 2. You can't incorporate these into some new constant. Now, you can check this on your own, and you should go back. If you plug this in for x and this in for y, back up here in this original system of DEs, so you'd have to take the derivative of x with respect to t, derivative of y with respect to t. Both of those equations, we got both of those solutions will satisfy these two equations. Okay, now real quick, let's solve an IVP. Because why not? So let's assume that we have, say, x of 0 equals 2 and y of 0 equals 4. If we're going to solve an IVP, even if we were given this information at the beginning, we have to wait until the very end to do it. Okay, so we're literally just solving for C1 and C2 now. So x of 0 means plug in 0 for t. 3c1 e to the 0t, that's just 1, plus c2 e to the -0, that's going to be a 1, y of 0, oh, and that's supposed to equal 2, x of 0 is 2, e to the 0, I'm plugging in 0 for all of my t's. That's supposed to equal 4. So now we get this system of algebraic, not a system of DEs. This is nothing complicated like what we had before. This is a college algebra system of equations. C1, 3c1 plus c2 equals 2. 2c1 minus c2 equals 4. I'm lazy. I would just solve this by elimination. If I'm not going to go through all the work of plugging this in my calculator, I would just solve it by hand, because if I add these together, the c's cancel out. I get 5c1 equals 6. The c1 is 6 over 5. And then let's see, if we plug that in here, I'll get 18 over 5, multiplied it by 3, plus C2 equals 2. So C2 will be 2 over 5, which is 10 over 5, or 2, which is 10 over 5, minus 18 over 5. So negative 8 fifths. So then my particular solution would be x equals 3c1, 18 over 5, e to the 4t, plus c2, e to the negative t, and y will be 2 and negative 1, 2c1. So twice that guy will be 12 over 5 e to the 4t. Keep forgetting what it was. Minus c2, so minus a negative, plus 8 fifths e to the negative t. And that is a good place to stop.